So we'll see the problems on these generators. Problem number 1. A 4-pole armature of DC machine has 1000 conductors and a flux per pole is 20 milliweb. Determine the EMF generated when running at 600 revolutions per minute when the armature is first wave wound, second one is lap wound. Solution. The given data, first you have to write the given data. P is equal to 4 number of poles, Z number of armature conductors 1000, flux per pole it is given 20 milliweb, 20 into 10 raised to minus 3 web, and N, so that is the revolution per minute, RPM it has been given, that is 600. If you want you can convert into revolution per second. So revolution per second also you can convert. First question is as a wave wound what is the EMF generated? So for a wave wound, number of armature path is equal to 2. That is already seen while solving the derivation for EMF equation for a DC generator. For A is equal to 2. So while substituting the equation, so E is equal to 5Z NP by 60A. So generated EMF, the formula, pole 4, flux 5 has been given, N 600 RPM, number of conductors 1000 into 60 into 2, E is equal to 2 for a wave wound. So we will end up with 400 volts. Second is while lap wound, what is the EMF generated? So for lap winding, A is equal to P, number of parallel path is equal to number of poles. So this P and this A will get cancel each other and we will get answer as 200 volt. Problem number 2. A DC generator running at 25 revolutions per second generates an EMF of 150 volt. Determine the percentage increase in flux per pole required to generate 180 volts at 20 revolutions per second. So you have to understand the problem now. So when it is running at 25 revolutions per second, the generator generates 150 volts. And when it is running at 20 revolutions per second, so it is generating 180 volts. If that is the case, what is the percentage increase in flux that you have to find out? So two cases he has mentioned. One is 25 revolutions per second and generating 150 volt, and the next is 20 revolutions per second and is generating 180 volts. And in between that we need to find out the percentage increase in flux per pole. Fine. So generated EMF E, so even if it is the formula is 5Z NP by 60A, so we can tell it is directly proportional to phi and omega. So omega is comes in rotations N, so 2 pi N, so omega comes N, so directly proportional to phi and N, phi into N. So omega is equal to 2 pi N, so where N is equal to RPS here. So because we can consider here RPS because the problem it has given in terms of RPS, not in terms of RPM. So we can consider phi E directly proportional to phi into N. So here E directly proportional to phi into N, and we can take PZ by 60A as a constant. PZ by 60A as a constant. Then so E directly proportional to phi into N. It is given it generates 150 volt at 25 revolutions per second. In that the case, what is generating flux per pole is phi 1. When it is generating 180 volts, N2, that is the speed is 25 revolutions per second, and flux per pole that we can take as phi 2. E1 by E2 is equal to phi 1 N1 divided by phi 2 N2. Because E1 is directly proportional to phi 1 into N1, E2 directly proportional to phi 2 into N2. General formula E directly proportional to phi into N. So we can write like this, that is 150 and 180 it has been given the problem, and 25 RPS and 20 RPS N1 and N2 it is also given in the problem. Phi 1 and phi 2, so that you have to find out phi 1 and phi 2. Whether it has also given, that you have to see. Determine the increase in flux, percentage increase in flux, so that you have to find out. How to find out phi 1 and phi 2? So phi 2, if we consider phi 2, you have to find out phi 2 in terms of phi 1, you will get 1.5 phi 1. While solving this equation, you will get phi 2 is equal to 1.5 phi 1. So phi 1 is initial flux produced, phi2 is the final flux produced. So that is in the problem. So percentage increase in the flux required to generate 180 volts at 20 revolution per second. So that is phi2, the second case. So by looking at this equation, phi2 is equal to 1.551, we can say that flux has increased by 50%. Otherwise it is 151, now it is 1.551, means the flux has increased by 50%. That's the answer. The third problem, a separately excited generator, is a DC generator, develops a no-load EMF of 180 volts at armature speed of 15 revolution per second and flux per pole is 0.2 Wb. Calculate the generated EMF when speed increases to 20 revolution per second and the flux per pole remains unchanged. So speed has been increased and the flux, it will not be changed. Initially it is generating 180 volts at a speed of 15 revolution per second. Flux has been given. Now you have to find out the generated EMF when speed increases to 20 revolution per second with flux unchanged. Second, speed remains 15 revolution per second. Speed will not change. The second case, flux is decreased to 0.125 Wb. Flux per pole is decreased to 0.125 Wb. Then you have to find out the generated EMF. The third case, speed is increasing and flux is decreasing. In that case, we need to find out the generated EMF. So we'll go for first case. In the first case, speed increases to 20 revolution per second and flux per pole remains unchanged. We have got our formula E1 by E2 is equal to phi1 N1 divided by phi2 N2. So that means E is directly proportional to phi into N. So E is directly proportional to phi into N, flux per pole and speed. So from this we will get this formula. If we substitute E1 is initially it is generating 180 volts E1. What is our E2? That we need to find out E2. You have to find out the generated EMF for this particular case A. What is that? Flux initially phi1. So it is flux is 0.2 Wb. Definitely phi1 is 0.2 Wb and it is running at 15 revolution per second, the first case. Now speed increases to 20 revolution per second, flux per pole is remain unchanged. That means phi1 and phi2 are same. Speed increases to 20 and we need to find out E2. So by using this equation we will end up with E2 is equal to 240 volts. Now coming back to the second case, now speed remains 15 revolution per second, flux is decreased to 0.125 Wb. Now once again we are adopting the same formula, 180 E1, 0.2 and 15, 0.2 flux, initial flux 0.2 Wb, 15 revolution per second. The second case, flux is reduced to 0.125 and speed unchanged. In that case we need to find out E2. So E2 will come as 112.5 volts. Third case, speed is increasing from the initial position and flux is decreased to 0.180 Wb. So we have got formula E2. Once again 180 by E2, 180 by E2. So 180 by E2 is equal to 0.2 into 15 divided by, this both are changing now, 0.18, flux is changed to 0.18 and speed is increased to 25 rps. So in this case we need to find out E2. So E2 will come as 270 volts. Problem number 4. A short shunt compound generator supplies 50 amps, because generator is always supplying current at 300 volts. If the field resistance is 30 ohm, the series resistance is 0.03 ohm and the armature resistance is 0.05 ohm, determine the EMF generated. So you have to find out the EMF generated for a short shunt compound generator which supplies 50 amps at 300 volts. So this is very important. You have to understand the problem. What is meant by this? 50 amps at 300 volts. It supplies 50 amps at 300 volt means it is coming at the load side. The 300 volts is the terminal voltage V and 50 amps is the load current 50 amps. It supplies the load current 50 amps. That you have to understand. And we need to find out EG, EMF generated in a sense EG. And to that field resistance, that means to say shunt field resistance has been given 30 ohm and series field resistance is 0.03 ohm and armature resistance RA is equal to 0.05 ohm. And also we should know that compound generator is a combination of shunt and series field. So that you can observe here, but is once again the short shunt. So this is the shunt field generator. The shunt field is parallel to armature only. Even if both series and shunt field resistance are present here, this shunt field is parallel to armature only. So here, so this voltage this is given as 300, and definitely there is a voltage drop here, because as far as the resistance is there, when current is passing through this resistance, there is a voltage drop here. There is a voltage drop. So IL into RSC, so 50 is equal to load current which is flowing through RSC. So 50 into 0.03, 1.5 volts. So there is a drop in voltage in a series field resistance. There is 1.5 volts. It has been given. Potential difference across the field winding, that is equal to potential difference across the armature. So that means to say, so this voltage is same as this voltage. Potential difference across the armature is equal to potential difference across the field winding, because these two are dead parallel. So V1 is equal to 300 plus 1.5. So this voltage 300, that is already given. It is supplying 50 amps at 300 volt. So that means to say load side voltage, it has given 300 plus, now it is adding. So 1.5 volts, it has been added here. So total 301.5 volts, it is coming across here. That you have to understand. So that you have to understand, because you can take this series field winding here. If you take the series field winding here, so there is a voltage drop here, there is a voltage drop across the load. So total voltage drop 300 plus 1.5, so that is 301.5. so that is total voltage across here. So armature, so that is it is coming here. So total voltage drop, so this plus this will give here this voltage drop 301.5 volts. Now once we found out that total voltage drop is 301.5 volts, field current IF is equal to V1 by RF. So once we found out that this is the voltage, total voltage across the armature, this is the total voltage across armatures. So this is the total voltage across because this resistance plus so this resistance, if we come total voltage, so this is the total voltage 301 here, 301.5 volts. So this 301.5 volts, it is coming across armature, also it is coming across the shunt field resistance. So from this we can find out shunt field current as 301.5 divided by 30. So 30 is the shunt field resistance. It has been given in the problem. We'll get 10.05 amps. What is armature current? ISH plus IF or ISC. So what is ISC and IL are same. So IL 50 amps, IF they already found out. Total 60.05 amps is the total armature current. So total armature current is this plus this current, ISH plus IL. So or IF. So is equal to 10.05 amps is equal to 60.05 amps it will come. Now what is generated EMF in a generator? So generated EMF is equal to, so V1 plus IRA. So generated EMF EG is equal to V plus IRA. This V plus IRA will give the total generated EMF. So that is general formula for a generated EMF EG is equal to V plus IRA. But here V is our V1. So this 300 plus this, the voltage drop across series field, it is equal to V1 plus IRA drop across armature resistance. So definitely it will be there. So total V1 plus IRA will give the generated voltage E. So that is 301.5 plus IA. They are already found out 60.05 amps into armature resistance has been given 0.05. So total it will come as 304.5 volts. So like that we need to calculate. Problem number 5. A DC generator has a generated EMF of 210 volts when running at 700 revolution per minute and the flux per pole is 120 milliweb. Determine the generated EMF at 1050 revolution per minute, that is RPM, assuming the flux remains constant. B. If the flux is reduced by 1/6 at constant speed, we need to find out generated EMF. Third point, at a speed of 1155 revolution per minute and a flux of 132 milliweb, we need to find out the generated EMF. So there are three cases that we need to find out the generated EMF. The data has been given. The generator has a generated EMF 210 volts when running at 700 revolution per minute. That is the initial case. If you are considering this as E1, if you consider this as N1, so these are the initial cases when generator is running at 700 revolution per minute RPM and is generating voltage of 210 volts. Flux per pole, in that case it has been given as 120 milliweb. Fine. We need to find out the generated EMF for this condition, 1050 revolution per minute, assuming flux remains constant. So you can use the general formula E1 by E2 is equal to phi1 N1 divided by phi2 N2. But this phi1, so there is RPS. So that we need to convert to RPM. So we need to consider RPM 700 by 60. So 700 by 60 we need to convert. So anyway it will cancel, even if you straight away to convert 700 and 1050 also we can consider. So we can consider this as capital N1 and N2 also we can consider. So initially E1 210 divided by E2, that is equal to phi1 is given 120 into 10 raised to minus 3, 120 into 120 milliweb initially, divided by phi2 120 10 raised to minus 3. It has been given that flux remains constant, so there is no change in flux in second case, and 700, and here it is given as 1050. So by solving this equation, so we will get as E2 the generated EMF as 315 volts. Second case, when it is generating an EMF of 210 volts and running at 700 revolution per minute and flux per pole is 120 milliweb, and second case is if flux is reduced by 1/6 and constant speed. So speed is constant. In the second case speed will not change. That means see here the speed will not change. The second case you have to use the same formula, E1 by E2 is equal to phi1 N1 divided by phi2 N2. So E1 it will not change, 210 only initial voltage, initial speed 120 into, now so that you have to understand 120 into 10 raised to minus 3. So that is E1 by E2 is equal to phi1 N1 by phi2 N2. So phi1 is equal to 120 milliweb into N1 700 divided by 60 converted into RPM, and E2 that we need to find out phi2. So phi2 reduced by 1/6, reduced by 1/6. So that is 5 by 6. The remaining is 5 by 6. Reduced by 1/6. The remaining is 5 by 6. So that you have to understand. Reduced by 1/6 in the sense the remaining is 5 by 6 into that particular flux 120 milliweb into, it will remain same, constant speed, it will remain same. So by solving this we will get E2 as 175 volts. The third case, speed will change, flux is also changing. Speed and flux both are changing in the third case. For that we need to find out E2. E1 remains constant, phi1 and N1 remains constant, and second case phi2 and N2 both are changing. So in that case we need to find out E2 as 381.2 volts. So in this case 132 milliweb and 1155 revolution per minute. So in that case we will get EMF as 381.2 volts. Like that we need to solve. Problem number 6. A 15 kilowatt shunt generator having an armature circuit resistance of 0.4 ohm and field resistance of 100 ohm generates a terminal voltage of 240 volts at full load. With the shunt generator, armature resistance has been given, shunt field resistance has been given, and terminal voltage V 240 volt has been given. Determine the efficiency of a generator at full load, assuming iron, friction and windage losses are 1 kilowatt, total 1 kilowatt. All losses altogether is 1 kilowatt. So that you have to understand now. So how we can find out now? So we need to find out the efficiency. So but what is the formula for efficiency that you have to understand? Efficiency is equal to output divided by input, one formula, into 100%. One is output divided by output plus losses. Input I can write it as input as output plus losses. So that formula that we are adopting here, output divided by output plus losses. What are the losses here? What are the losses? IA square RA loss, I square R loss, and field circuit resistance loss. So that you have to add in here. So plus other losses, it has been given here, friction, windage losses, total 1 kilowatt it has been given. The formula says output divided by output plus losses. So let's see how all these things can be calculated here. So now for this to calculate, we require IA and we require IF field current, we require armature current, then only we can do it. How we can find out armature current? We know that armature current for a shunt generator is equal to IL plus ISH, IL plus ISH, or IF field or ISH. Field current IF we can call, or ISH shunt field current also we can call, I or IL. So IL plus ISH. So how we can find out now IF or ISH? We can find out ISH as V by RSH. So this is a formula for find out IF or V, voltage V by RSH. It will give ISH or IF. V is the terminal voltage 240 volt, it has been given, divided by shunt field resistance 100 ohm, it has been given, and we will get 2.4 amps. Once you get 2.4 amps as IF, IA is equal to IF plus I. What is I? What is I? It is a load current. I is equal to load current. This I or IL. So how we can find out IL? IL is equal to 15 kilowatt. The power is been given, divided by voltage 240 volt. Power by voltage will get load current 62.5 amps. It has been given as IL. Once you find out IL, once you find out IF, so this is 15 kilowatt generator and terminal voltage 240 volt it has been given. So load has been given and terminal voltage has been given. We can find out the load current. So this is 15,000 divided by 240 will get 62.5 amps. That is load current here. So once you find out IF, once you find out IL, IA is equal to IF plus IL or ISH plus IL, we'll get 64.9 amps. Once you get IA, then we can use this formula, output divided by output plus losses. What is output of a generator? V into I. So V is a voltage into load current. So that is output of a generator. So that is given as 15 kilowatt output. Straight away it is given in the problem, output as 15 kilowatt plus output plus losses. Once again 15 kilowatt plus losses. What are the losses? So losses can be in the armature as well as shunt field. So all losses we need to calculate. What is the I square R loss? So I square R loss is armature copper loss. So IA square into RA plus shunt field loss. So losses are in terms of watts. So voltage into current. Voltage into current. IF is the shunt field current into V. So 240. So this full voltage is coming across the shunt field. So we can consider this voltage drop across shunt field also 240 volts. So 240 into shunt field current. That is a loss. Shunt field loss. This is also watt. I square R. The shunt field loss plus other losses 1 kilowatt, it has been given 1000. So all, if you substitute, we will get efficiency as 82.14. Like that we can solve the problem.